Let us continue the discussion of time response of the RC network, which is given by this circuit diagram. So we have actually found the transfer function of this, which is given by, of course, for unit impulse input, it is 1 over 1 plus s tau, so which we are trying to find what is the response of this, that is the time response of the output voltage. So now let us consider the example of R is equal to 1 k, C is equal to 1 microfarad, and try to find out what is the output of this circuit for a delta function unit magnitude. So now this is the input what I am considering. This is T. At T is equal to 0, I have a unit input. So having this type of unit input. So for which I'm supposed to find if the value of R is equal to 1 kilo ohm and C is equal to 1 microfarad, the tau which happens to be R into C will become 1k into 1 micro. This will become 1 milli. So now tau is equal to 1 milli. So R, which is 1 e power minus 3, or 1 into 10 power minus 3. So now it is Laplace inverse of 1 into 10 power minus 3 divided by, so this is 1 over. So of course we know that 1 over 1 into 10 power minus 3 happens to be 1000. So that I can write as Laplace inverse of 1000 divided by 1000 plus, yes. So now you can simply write this Laplace inverse of this is 1000 e power minus. Okay, now we know that it is something like this. So it is e power 1 over Laplace inverse of 1 over s plus a is nothing but e power minus 80. So in place of a I have 1000, it is t into 1000, or I can write it as 1000 e power minus e by 1 milli. Of course 1 over only is nothing but 1000. So this is what is V naught of t. This is what is V naught of t. So meaning I can actually able to find the output voltage at different times. So maybe you can say I can write a table consisting of, for different time I can find out what is V naught of t. Maybe you can start from 0. So at time t equal to 0 for this input. So suppose if you substitute t is equal to 0, then this becomes 1. So this is 1000. Suppose if you take t is equal to maybe 1 milli. Suppose if you take after 1 millisecond, what happens? So I can actually substitute this. So this is 1 milli, that is 1000. So that will cancel out. It is 1000 e power minus 1. So now this will become 367.8. So maybe at 10 milli. So at 10 milli this happens to be, okay, now this will become 10. So I can find out how much is this. So it is 0.0453. So meaning as the time elapses, so from at t is equal to 0, it has got a magnitude of 1000. Let me write the response of this. The response of this would be at t is equal to 0. At t is equal to 0, it will going to have a magnitude of 1000. As t increases, at 1 millisecond itself, the magnitude has reduced from 1000 to it will become 367.8. So maybe at 10 millisecond, the value is 0.043, meaning it exponentially reduces. Meaning the response of this for this circuit, if I apply, of course this is a very imaginary signal what we are talking about. This will never exist in real time. This is t at 0, and if this is RC, if R is equal to 1 k, this is equal to 1 microfarad. At this point, if you measure, this is an imaginary signal which you will never realize. So you will end up with a signal starting at 1000, t is equal to 0, and it drops so fast. This is when it is equal to 1k and when it is equal to 1 micro. Suppose assume that this is 10k. it is 10k and 1 micro, then what happens to tau? Tau will become 10k into 1 micro. This will become 10 milli. If it is 10 milli, so what is 1 over 10 milli? So 1 over 10 milli will become 100. So let me just make it exponential of minus 3. 1 over that will become 100. See now, in such case, suppose if you are having RC network, if you are having a RC network of R is equal to 10 kilo ohm and C is equal to 1 microfarad, if you apply an input which is a delta function, which is again an imaginary input, how does the output looks? The output would be on the same lines. Instead of 1000, this will become 100. It will become 100. So this will now become. So now this will become 100 e power minus t into 100. So now the initial magnitude is 100. At larger values of t, this comes down. This comes down. Here, this is keep. This is at t is equal to 0. This is for large values of t. You can actually find out, as we did here, for different times. You can find out what is V naught by substituting this into this equation with this as 100. With this as 100. That's how the time response of a first order system, because why it is first order, because it's v naught of s by v in of s. The transfer function is 1 plus src, 1 plus src, which is nothing but first order system. Now to the same first order system, if you apply a step input, how it looks. This again, because we are dealing about the time response of a system, time response of a system, because as we discussed, so there are different types of inputs possible. So let us just refer to only these two inputs, like inputs and step input. Now if I give a step input something like this, how the response of the system is. RC, let us again take it as 1 kilo ohm and this as 1 microfarad. Let me apply input which is something like this, which is having a response. This is my input. So this has got the input of 1 at t is equal to 0 and greater than that, and it is 0 for values of t less than 0. So this is v naught t and this is v naught of t. So I'm looking at what is v naught of t, which is nothing but Laplace inverse of v naught s by 1 plus src. Correct? This is what I have as the equation. Okay, which is already originated from our earlier discussion. This was the transfer function. So it is 1 over. This is v naught of s. Now it is this is the expression what you have. So for v in of s for a step input. So what is v in of s for a step input? So this is v in of t. This is v in of t. It is a unit step input. Then v in of s will become 1 over s. So that's what we discussed here. If the input is a step input, its Laplace is 1 over s. If it is an impulse, its Laplace was 1. So that's why we substituted 1 in the previous case. Now since it is step input, v naught of s becomes 1 over s. So what is v naught of t now? V naught of t is Laplace inverse of what is v naught of s? It is 1 over s multiplied by 1 over 1 plus src. This is the expression what I have. So what is v naught of t? It is now Laplace inverse of 1 over s into 1 plus s. Let me say it as tau, because RC we usually write it as tau. Now you don't have a direct Laplace inverse of this, so I have to rewrite this 1 over s into 1 plus s tau using partial fractions. I can write it as a by s plus b by 1 plus s tau. So it is equal to this. So now upon simplifying, I can write it as a into 1 plus s tau plus b into s as equal to 1. This is my equation. So now I have to solve this equation to get the values of a and b by equating the quotients of s and s power 0. So now the quotient of I can rewrite this expression as it is A plus uh, B in okay B plus A tau into S. So this is grouping the coefficients of S and h power 0 is equal to 1. So it's actually, this is like okay 0 into s power 1. So this is, now what is the coefficient of h power 0? It is 1 here, it's here. So a is equal to 1. If a is equal to 1, by equating the coefficients of h power 1 on right hand and left hand side, it will become a tau, because b plus a tau is equal to 0. So what is b is equal to? B is equal to minus of a tau. Correct? So now this is correct. So this is what you have. So you have this a is equal to, so but what is a? A is equal to 1. Shall I write b is equal to, b is equal to minus tau? I can write b as equal to minus tau. So what we had v naught of t as equal to Laplace inverse of 1 over s into 1 plus s tau. It can be now written as Laplace inverse of a is 1 by s, t is actually minus tau by 1 plus s tau. The equation what you have. So I want to find the Laplace inverse of this. So I can write v naught of t as Laplace inverse of 1 over s and minus of Laplace inverse of tau by 1 plus s tau. Correct? That's how I can easily write. So I know the Laplace inverse of 1 over s is 1. What is Laplace inverse of this? So let me just rewrite this as tau. Let me take tau outside. So can I write it as 1 over tau plus s? So then this tau and tau will go off. So what is this Laplace? This is 1 minus Laplace inverse of 1 over s plus 1 over tau. So this is now equal to 1 minus. So we are still now dealing with v naught of t with v of uh, s as equal to 1 over s with v of t as u of t, a unit step function. It is 1 minus. So what is this? This is actually e power minus t by tau. So what is the output now? So output is 1 minus e power minus t by tau. What I mean to say is, of course, this is a very straightforward one. So we started with this RC network. We are trying to find what is the output voltage for an input of 1 over s, which is the Laplace of uh, unit step input. We are trying to find the Laplace inverse of V of s by 1 plus SRC. So we are ending with this. So we have this equation. So we are using partial fraction. We are writing this, trying to find the values of a and b. Once you get the value of a and b, you can get what is v naught of t. So v naught of t is now given by this. So which ultimately comes like 1 minus e power minus t by tau. So now let us take the example of a particular example of R is equal to 1 kilo ohm and again C is equal to 1 microfarad. This is V naught, this is V in, this is a step input, this is 0 at 1. Now I want to know what is the output. So now how does the so what is V naught of t? V naught of t is equal to 1 minus e power minus t by tau. So what is tau? Tau is equal to R into C. So with this R is equal to 1 and C is equal to 1 microfarad, that is 1 can 1 microfarad will give me 1 millisecond. So now this will become 1 minus e power minus, okay, 1 over only is 1000. It is 1000 t. So this is V naught of t. So this is my expression. So let me try to know what is the output at different timings. Again, so let me know at t what is V naught of t. At t is equal to 0, what is the value, and at t is equal to 1 microsecond, what the value, maybe at 10 microsecond, what the value, maybe at 1 millisecond, what the value, maybe at 10 millisecond, what the value. So I just want to know for a input voltage which is step input, this is t 0. So let us try to find what are the values. So now what I have, so let me just take it as 1 minus okay, this is minus of 1000 into alpha a. Calculate for alpha is equal to 1 exponential minus 6. So now let us give it for 0 it is. So for 0 what's the value? So when you have e power 0, e power 0 happens to be 1, so 1 minus 1 is 0. So you can see this will become 1, so 1 minus 1 is, so this is 0. So output voltage is 0 here, output voltage is 0 here. So let me just give it as, okay, let me just close the parenthesis here, e to the power of minus 1000 into alpha a, close the parenthesis, calculate, okay, or even let me give it as zero point 0.1 micro. So maybe let me give it as 0.1 exponential minus 6. So sorry, something happened. So let me just repeat, 1 minus alpha, this one, minus of 1000 into alpha a, close, calculate for 0.1 exponential minus 6. So when it is this, it slightly reduces, sorry, at 0.1 microsecond, its value is 9.9 e power minus 5. Calculate at 1 exponential minus 6. At 1 microsecond, its value is 9.95 into 10 power minus 4. Calculate at 10 exponential minus 6, you can see it is 9.95 into 10 power minus 3. This is 10 power minus 3. It's increasing. Calculate at 1 millisecond. At 1 millisecond, it is 0.632. Calculate at 10 millisecond. 10 millisecond, it is 0.9999. So these are the values of your output voltage as time increases beyond 0. You can see it's actually going like this. This is actually going like this. So what is this? Your output voltage is exponentially increasing. This is V naught of t. I'm just approximately writing. You can see it's like 10 power minus 5, 10 power minus 4, 10 power minus 3, then it is 0.632, then it is 0.998. So by this time, so the time is 10 millisecond. By 10 millisecond time, it has almost reached a magnitude of 1, that is 0.9999. What I mean to say is, the time response of a first order RC cycle for a unit step input has got this type of expression or the output response. So for different tau value, for different timings, so tau actually corresponds to R and C values. Suppose if you have larger value of R and C, then the charging would be slower. Charging would be slower. If you further reduce the, if you further increase the value of R, it just decays or charges slowly. If you reduce the value of R, then it charges quickly. It charges quickly. So this is a different. If I say tau 1, tau 2, tau 3, tau 4, if I write the relation tau 1, tau 2, tau 3, tau 4, tau 1 has got largest time constant, so this is greater than this, greater than this, greater than this. Tau 3 has got the least time constant, that is the lesser value of R and C, so that it charges quickly, so that it reaches the final value quickly. This is how we can find the time response of a system, first order system. First order system. Sorry. Let me move on to the. This is 4. This is okay. 5, 6, 6 and 7. Let us move on to second order system. Let us move on to time response of second order system. So this is a very standard. It's not like, okay, in control system you do it for first order, then second order, then third order, fourth order, fifth order. We stop it at second order because any higher orders of the system will consider the dominant poles. So where the dominant poles will be only 2 poles. So that's why the time response of control system stops at second order. So we know that for a second order system, uh, CFS by RFS. In general representation, we write it as omega n square plus s square plus 2 zeta omega ns plus omega n square. So by this time you already know what is omega n, what is zeta, all those stuff. I will not go into the details of that. So now, of course, this can be realized using a RLC circuit, something like this. You can have R here, L here, you can have a capacitor like this. So this is R, L, C, right? This is V naught, this is V in. So you can actually get 1 over LC by, if I'm not wrong, it is S square plus 1, 1 over LC, and this is S, uh, S R by, okay, this let me just, okay, confirm. Again, I don't want to remember the equations. Maybe you can just, okay, try out what is possible transfer function of that. So I'm just looking into one of the material where I have the transfer function of that RLC circuit. Now you have this as R by L. Okay, I'm just referring to this. So this is my circuit. So this is RLC circuit. The output is taken across the capacitor. V naught of S by V in of S is 1 over LC S square by R by L into S plus of 1 over SC. Fine. So in this, we know omega n is 1 over root of LC. Then 2 zeta omega n happens to be R by L. So if you want to find what is 2 zeta, then that will become R by uh, L omega n. So what is omega n is actually this will become R by L. So 1 over omega n will become, that is root LC, and this will become, so here you can write it as root L. So then this will go with this. So then this will become R. Okay, then zeta will become R by 2 under root of C by L. So this is my zeta value. So meaning for a given RLC circuit, you can find what is the value of omega n, which is given by under root of LC, and you can estimate the value of zeta, which is nothing but R by 2 root of C by L. This is the relationship between the equation and the components of RLC network for a second order system. So now what is interesting here is, so we are looking at a system which is something like this. So maybe you can also represent a second order system by a block diagram, something like this. So this is like omega n square. This is S into S plus okay, this is 2 zeta omega n. So this is the equation. What I have is this. So this is minus. If you are writing it's okay, this is RFS, this is CFS. If you consider the feedback system, the closed loop feedback, then CFS by RFS will become omega n square by s square plus 2 zeta omega ns plus omega n square. So this is my second order standard equation. Now I want to know what is the response, the time response of this system for a step input. This is my R of t. This is t at t is equal to 0. It goes to 1 and it is a unit magnitude. I am trying to know what is, of course, this is nothing but Laplace inverse of R of s into omega n square by s square plus 2 zeta omega ns plus omega n square. So you need to find the entire Laplace inverse of this, which is a lengthy mathematical process to find out what is C of t. I'll be writing the final expression and we are trying to understand what is the uh, parameters of each parameter of that time response. It is given by C of t is equal to 1 minus e power minus zeta omega nt divided by under root of 1 minus zeta square. So, so this is into 1 minus sine omega d. Okay, this is sine omega dt plus theta. There is no 1 minus. It is sine omega dt plus theta. The time response of a system is given by, so it is 1 minus e power minus zeta. That's the equation what we have. Uh, Suppose if I want to write what is the response of that system for a step input. So let me just write the response of that. Give me a minute. Let me just take an example and try to give you. Okay. So now this is the expression for 1 minus e power minus zeta omega nt under root of 1 minus zeta square sine omega dt plus theta. So let us try to understand what does each term corresponds to and what is the significance of that. So as we know, C of t is given by 1 minus e power minus zeta omega nt by root of 1 minus zeta square sine omega dt plus theta. Now, this is valid for underdamped system. Underdamped system. So, what do you mean by underdamped system? The value of zeta is between 0 and 1. It is not 0, it is not 1, it should be between 0 and 1. It should be between 0 and 1. So now, as we know, this is our closed loop transfer function. So, it is going to have the root. It is going to have the roots. The roots will be, where are the roots? The roots will be here like this. The roots will be always complex in nature. Roots are always complex in nature. So now this is the real part. This is omega, and its real value will be, so this is minus zeta omega n, whereas of course this is omega n, this magnitude, whereas this is under root of 1 minus zeta square into omega This is what I call it as omega d. What is this omega n? Omega n is the natural oscillating frequency in radian per second. Omega d is damped 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 oscillating frequency. Damped oscillation frequency. So this is also in radian per second. Zeta is damping factor. Damping factor. This is a unitless quantity. So now what is the position of this one? So the real value of the complex roots are minus zeta into omega n, whereas the imaginary value is plus or minus j omega n into root of 1 minus zeta square. These are the two roots. So this is for minus zeta omega n plus of j omega n and root of 1 minus zeta square. This is minus zeta omega n minus of j omega and root of 1 minus zeta square. These are two closed loop poles if the value of zeta is between 0 and 1. So now, where are the poles if zeta is equal to 0? If zeta is equal to 0, then this becomes 0. When this becomes 0, then what will this become? If zeta is equal to 0, then this will become minus 0 plus or minus j omega n root of 1 minus 0. So this is having roots plus or minus j omega n. So meaning zeta 0 means it's an undamped oscillations. That is, this is equal to omega. So there is no damping, undamped. So this is called undamped. So undamped is nothing but omega. So that's what is this omega. The poles will be over here. So it will be on the imaginary axis. If zeta is equal to 1, if zeta is equal to 1, then this becomes 0. When this becomes 0, you have minus zeta omega n. So this minus is 1 means, sorry, if zeta is 1 means, then it is minus omega n. So you have repeating poles at minus omega n. That is when the value of zeta is equal to 1. This is when zeta is equal to 0. So that's why while writing the pole position, closed loop pole position of a second order system, we take this as semicircle. This is a semicircle now. So this is minus omega n. This is omega. That's why the radius of this is always omega. So the poles can be here, poles can be here, poles can be here also, poles can be here, and poles can be here. This is what is the possible values of zeta, possible values of closed loop positions for the different values of damping factor zeta 1, zeta 2, zeta 3. Suppose if you want to get the relation between zeta 2, zeta 1, zeta 2, zeta 3, see here zeta is 0. So zeta 1, zeta 2, zeta 3. Actually zeta 1 is the least. So zeta 1 is lesser than zeta 2, zeta 2 is lesser than zeta 3, zeta 3 is the highest one here. Even when I say highest, when it is complex, the value of zeta is still less than 1. So that's why zeta value, if it is between 0 and 1, the poles are always complex. So whatever response we write here, whatever time response we write here is only valid for values valid for zeta between 0 and 1, which will result in complex poles. If zeta is equal to greater than 1, then this equation is not valid. This is valid for only zeta between 0 and 1. Even it is not equal to. If it is equal, then this will become 0. Then this is not a valid equation. Then it will be sine omega t. So that will be the oscillating frequency. So now, what is this theta? You have this theta, no? This theta. This theta is nothing but, supposing that the poles are here. The poles are here. These are the complex poles. So assume that you have this as this is maybe assume that this is minus omega n. This is omega d plus j omega d. So what is this? So this, there is an angle here. So there is an angle theta. So this angle is theta. So what is theta? Theta is nothing but, so can I say this is omega n, we know. So what is sine theta? So we know that sine theta is equal to opposite by hypotenuse. So what is opposite? It is, so sorry, you have, so we write, so let me write it as, what is cos theta? So cos theta is nothing but adjacent by hypotenuse. So what is adjacent? Of course, just the magnitude. zeta omega n. What is hypotenuse? It is omega n. So does this go with this? So then cos theta is equal to zeta. Or shall I say zeta is equal to cos inverse of theta? Meaning, if you know where the complex poles are, if you find this angle theta, then cos inverse of theta will be equal to theta, So that's how you can easily find the value of zeta from the given pole position. Okay, this is about these parameters. Zeta is damping factor, omega n is natural frequency, of course t is with respect to time, and this is theta is nothing but the angle subtended by the complex pole from here. Again, theta can vary from uh, greater than 0 to less than 90 degree. If it is 90 degree, then the poles are on the imaged axis. If theta is 0, then they are repeating at minus omega. So these are the two extremes of theta value. Theta value is between uh, okay, this is greater than 0 but less than 90 degrees. And now let us try to find out what are the constituents of this time response of a second order system. This is the input R of t with magnitude 1. So we will end up with the time response of the system, something like this. So it is a damping one. It exactly goes like this. For an input which is given this. Now here we define, which you already know, this is the rise time, this is the peak time. Of course, this is your first peak, you can say TP1. This is, maybe you can say this is maybe TP dash 2. TP dash matlab it's a minimum. Again here it is TP3. This is TP4 dash. So when I say dash, it is the minimum. So when I say TP, it is maximum. So it is maximum, minimum, maximum, minimum. Don't so you get it. Of course, we know that it will settle down to the final value of t is equal to infinity. You cannot wait till there. So that's why we say 5% tolerance, and of course you're going to have 2% tolerance band. So that's what we have. PS 2% and PS 5% tolerance band. And we will also define one parameter called as MP, the maximum overshoot. So all of you by this time know what are the expression for all those parameters. So PR is nothing but pi minus theta by omega d, whereas T is equal to pi by omega d, and TS maybe 5% is given by 3 by zeta omega n. TS 5 2% comes out to be 4 by zeta omega n. So these are the typical uh, expressions. So now you have to be very careful while substituting this theta. They should be in radians. Because this is already in radian, because it is 3.14. You write it in, this is in radian. And when you say this is radian minus radian is radian unit. So here it is radian per second, then this will become in terms of second. Suppose if you substitute theta in degrees itself, then you'll end up with some negative 10, which is not a valid one. Again, we have the MP expression. MP is given by e power minus zeta pi by 1 minus zeta square and root of 1 minus zeta square. So these are all very standard equations what you have for this particular time response of a system for a second order system. Now let us do one or two problems and try to identify what is the different parameters of. Okay, we know that okay, this is what I said as TP, this is pi by omega d. If you want to find for this, so this here actually it was actually n pi by omega d. If n is equal to 1, you'll get this. For n is equal to 2, you'll get this. For n is equal to 3, you'll get this. For n is equal to, because it's like this, okay, 1, 2, 3, and then this is n is equal to 4. If you want to know what is tp dash 4, that is second value, second minimum, so then you have to substitute 4 pi by omega t. If you want to know what is the second peak, then it is 3 pi by omega t. So this is first one, then this is second, and this is third, fourth. So that's what is for every n it goes to uh, first it is peak, then it is the minimum, maximum, minimum, maximum. Because it's not the maximum anymore, but it is the next peak. So let us try to find out what is the typical. Let me just consider CFS by RFS of a system as 100 by a square plus 4s plus 100. Equate these to a standard function omega n square is equal to a square, sorry, omega n square by 2 zeta omega ns plus 100. So omega n square equating the denominator and their coefficients. So omega n square, sorry, this is omega n square. So omega n square is 100, so that you can write omega n is equal to 10 radian per second. So then what you have? You have 2 zeta omega n as 4. Then you can write zeta is equal to 4 by 2 into 10, which is 4 by 20, which is 1 by 5, which is 0.2. This is the value of zeta. So once you know what is omega n, which is 10, and zeta as 0.2, you can actually locate the poles also. Where are the poles? The poles are at -2 is the real part, and the imaginary part would be, what is imaginary part? So it is -2 plus or minus of j plus or minus j. It is omega n under root of 1 minus zeta square. That is 10 into under root of, sorry, under root of, sorry, this is under root of 1 minus 0.2 whole square close. So that will be 9 point, it is -2 plus or minus j 9.79. So this is the pole position. So this is at plus j 9.79, this is at minus j 9.7. Because the value of zeta is 0.2, it is closer to imagined axis, closer to imagined, that is closer to 10, closer to j10. And then let us try to find out what is the other parameters. So then what is rise time would be pi minus theta by omega d. Tp is pi by omega d. Ts would be for 5% 3 by zeta omega n. Ts is equal to, for 2% it is 4 by zeta omega n. So now, of course, this is valid for certain values of zeta. So we are just approximating it to Ponto. So we are taking the same expression irrespective of the value of zeta, but as per the textbook, it just goes with for a certain range of zeta only this is valid. If I can very clearly say that this is valid for only the value of zeta between 0.68. If the value of zeta is beyond 0.68, it's not valid. Maybe for 0.2, this is still valid. So 2% tolerance is 4 by zeta omega, and it is valid from 0 to, for anything greater than 0 to less than 0.8. It is still fine for 0.2 as the value of zeta. So now what is theta? So theta is cos inverse of zeta. So now what is cos inverse of 0.2? It's actually 88.85 degrees. So this into pi divided by 180. So this will become 1.55 radian. So then it is alpha, sorry, so it is minus 1.55 divided by omega d. You need to find omega d happens to be omega n into 1 minus beta square. So it is 10 into, I thought we already found, no? So it's 9.5, 9.79. So it is now, so it is minus 1.55 divided by 9.79. So it is 0.162 second. So then what is pi by omega d? Then pi by omega d is, so it is pi divided by omega d is 9.79. So this will become 0.32 second, and this is 3 divided by zero point 0.2 into 10. This will become 1.5 second. This will become, because in divided by 3 into 4, this will become 2 second. And what is MP? MP is e power minus zeta pi by 1 minus zeta square. This will be minus of 0.2 into divided by under root of 10 minus 0.2 square cube. So it is 0.5266, that is 52.66%. So if I give a step input for this, if I give a step input for this system, it will end up with a response something like this. So it will reach the rise time at, this is with respect to time, 0.162 second. It will reach the peak time at 0.32 second, almost the double. And this peak would be 1.526. That was, this is the peak value 1.526. That was, this overshoot would be 52.66%. Of course, it will settle down at 5% tolerance band at 1.5 second. It will take 2 seconds to settle within 2%. If you want to know what is this, then you have to find, you had this one, no? So this will become 0.64. And if you want to know this, it is 0.32 into 3. So that will become 0.96. And if you want to know this, so that's what is 0.32 into, this is 234. 0.32 into 4. That would be 1.28. So that's how it settles. So these are all different peaks and maximum minimum that you have to substitute this by n is equal to 1 here, here it is 2, here it is 3, here it is 4. This suppose I say it as 1 n value. Okay, fine. Then let us take a higher order system and try to find out the dominant force and its response. Let us consider a system which is something like this. So how do I take? Let me take a third order system. Maybe take it as 50 by s into s plus maybe 10. Let us see whether it is possible. Hopefully it is possible. Okay, this is my system. If it is not possible, let us change the parameters. This is system. I want to apply a step input. I want to see what is the response. I want to see what the response. So this is RFS, this is CFS, so that I can find what is CFS. This is actually RFT. One. Okay, fine. How do I do that? So, oh, let me just take a third order system. Sorry, S plus one. Okay, now this is my third order system. So this third order system will have del of S, that is the characteristic equation as S into S plus 10, S plus 1 plus 50. Correct? Because del of S is nothing but 1 plus g of s into h of s equal to 0. It's like 1 plus what is g of s? It is 50 by s into s plus 10 s plus 1. So equal to 0. Take the LCM, then it will come out with this. This is equal to 0. So what is this then? S into s square plus 11s plus 10 plus 50. Correct? So then this is s cube plus 11s square plus 10s plus 50 equal to 0 is my characteristic equation. Let me find the roots of it. If I find the roots of it, then this will become order 3. It is 1, 11, 10, then 50. I have pole at minus 10.50. Okay, other is at minus 0.249 plus or minus j 2.16. So I have the poles of this third order system. One is at minus 10.50 and other two are complex. Its real value is minus 2.49 and its imagined value is 2.16. So this is where the poles are. Now, even though it's a third order system, you have three poles here. Out of these three poles, these two are dominant poles. Why these two are dominant poles? Because they are closer to imagined axis. Since these two are closer to imagined axis, let me take what is this. So I have this as my transfer function. So where are the pole position now? The pole position is at minus 0.249 plus or minus k 2.16. Sorry, 2.16. So this is actually minus zeta omega n plus or minus of j root of 1 minus zeta square into omega n. This is actually the equation. So how do I actually find the pole position? Can I write the quadratic equation of this one? So I can write the equation of this as s plus 0.249 plus j 2.16 and s minus 0.249, sorry, s plus and minus of j 2.16. Correct? How do I find this is now resulting in a square plus as plus b. So let me just take this as a general form. So what is this a now? A is actually twice the real component, twice of 0.249. What is b? B is actually square of 0.249 square plus 2.161 square. So what is this b then? So it is now, so what is this? Of course, 2 into 0.249 would be, hey, sorry, let me bring it to 2 into 0.249. This is 0.498. How much will be this? 0.249 square plus 2.16 square equals 4.727. This is what is b. So then I can write it as a square plus what? A square plus 0.498 s plus 4.727 is equal to 0. This is my quadratic equation of these two dominant pairs. So this is the quadratic equation of these dominant pairs. So from which I can know what is omega n. What is omega n? It is under root of 4.727. So let me take the square root of answer. It is 2.17. This is 2.17 is omega n radian per second. This is, and what is zeta? Zeta is actually you have 0.498 by 2 into omega n. Omega n is how much? 2.17. So it is 0.498 divided by 2 into 2.17. How much is that? It is 0.114. So now it is okay. Now this is omega n is equal to 2.17 radian per second, and zeta is equal to 0.114. So now with these values of zeta and omega n for this system with these dominant poles, I can estimate what is the overshoot, what is settling time, what is peak time, all those stuff. Correct? So how do I do? So let me take again the same equation of PR pi minus theta by omega d. It is TP pi by omega d ts 5% p by zeta omega n. NP is e power minus zeta pi by 1 minus zeta square. So what is okay, we know that omega n is equal to 2.17 radian per second and zeta is 0.114. Okay, we already know what is omega d. This is actually zeta omega. This is actually minus zeta omega n. That's what is I have already written. So this is actually omega d. Omega d is directly available. So what is omega d? Omega d is actually 2.161, which will be almost equal to this into, you can approximately find 2.17 into under root of 1 minus 0.114 square should give me the same value. You can see you're almost getting that 2.155, which is this. So now what is theta? Theta is nothing but cos inverse of theta. So which is cos inverse of 0.114. It's almost closer to 90 degree. You can see it's almost 83.45 degree into pi divided by 180 is nothing but 1.45 radians. So that I can find what is this. That is pi minus 1.45 divided by omega d is 2.161. So this happens to be 0.782 seconds. So this is now it is pi by omega d is 2.161. It is 1.453 second. Settling time is 3 divided by 0.114 multiplied by 2.17. So it is taking 12 seconds. 12.12 seconds. So because this zeta is less, it won't have more overshoot. That's why the timings are more. So it's taking this much settling time. So how do I find this? It is now inverse minus of 0.114 multiplied by pi divided by, open the parenthesis, and the root of minus 1 minus 0.114 square, close, it is 69.73%. this, hopefully the calculations are correct. Let me just, maybe, let me just do it again. It is now uh, for E minus of 0.114 into, into, okay, pi, close the parenthesis, then divided by, okay, let me just open one more parenthesis, open 0.114 into pi, close the parenthesis, divide by, open, under root of 1 minus 0.114 square, close, yeah, it's fine. So it is this much. So now, even though this is a third order system, okay, now even though this is a third order system, we could able to find this as our dominant pole, and we have a response for this system as like this. So this is the response. So this will have a overshoot of 69%. If it is 1, then it will be 1.69, and it will take 0.78 second to reach the peak, sorry, the rise time. This is 1.45 second, and by around 12 seconds, it will reach 5%. By around 12%, sorry, by around sorry, by around 12 second, it will reach 5%, which is TR. That's what we wrote here. TR is 0.78. Peak time is 1.4 something, 1.45, and 12 second is the settling time, because it has got large, more overshoot, because the value of zeta is less. Zeta is less. Okay, this way we can able to find the response of even a higher order system, considering the dominant poles, which will be a second order system. Thank you. So in the next video, we will have a look at the steady state error of unity feedback system. Thank you.